In this video, we're going to look at the 2010 higher level physics paper and the question on particle physics. This was a full question, so worth 56 marks. The question starts off by telling us the history of antimatter begins in 1928 when a young physicist named Paul Dirac predicted an antiparticle for the electron. First off then, it asks what is antimatter. So antimatter, as a definition, the antimatter of a particle is a particle with the same mass and opposite sign of charge as its corresponding particle. It then says an antimatter particle was discovered during the study of cosmic rays in 1932. Name the antiparticle and give its symbol. So the first antiparticle discovered was by Carl David Anderson, and it was the positron, or the anti-electron. So that is E positive. So again, it's the same mass but opposite sign. An electron is E negative, so this is E positive. Then the question says, what happens when a particle meets its antiparticle? So when a particle meets its antiparticle, pair-annihilation occurs. And energy in the form of photons, which would be light, is created. So that's pair-annihilation. So that's what happens when a particle meets its antiparticle. So that's the first section, worth 18 marks, would be 3 by 6. The next question then says, what is meant by pair production? So pair production is a process where a particle and its antiparticle are created from energy. So pair annihilation is where they meet and give out light, and pair production is where they are made from energy, which typically be photons of light energy. So the question then tells us a photon of frequency 3.6 by 10 to the 20 Hz causes pair production. They ask us to calculate the kinetic energy of one of the particles produced, each of which has a rest mass of 9.1 by 10 to the minus 31. So the first thing I need to do is I need to get my formula. So when I see pair production, that is the energy of light, so energy E equals HF, so HF equals two particles, because it's got to create the particle and its antiparticle, mc squared, and then the extra energy, so some goes to create them and then some goes to move them. So we have EK1 and EK2, so they're the particles moving. So then I get my information organized. So H is Planck's constant, which I get at 6.6 by 10 to the minus 34 joules per second. The frequency I'm told is 3.6 by 10 to the 20 hertz. The masses are equal, so M1 equals M2, which are both 9.1 by 10 to the minus 31 kilograms. Then just to make my life a bit easier, I organize it here. The kinetic energy of one equals the kinetic energy of the second. So their combined kinetic energy I'm just going to call E to begin with. So I'm simplifying this formula to reduce down my constants, my variable side. So HF, which is our energy, that's equal to twice mc squared plus E. So I rearrange this, subtract that from both sides. So HF minus this is equal to E. So now that I have my information and my formula organized, I can sub everything in. So the energy is Planck's constant times the frequency minus twice by the mass by the speed of light squared. And when I throw that in, that energy is 7.38 by 10 to the minus 14 joules. That energy is the kinetic energy the particles will move with. So I take that figure, 7.38 by 10 to the minus 14 joules, and then divide it by 2 because I have my two different particles. So the kinetic energy of one is equal to the kinetic energy of the other, which is equal to 3.69 by 10 to the minus 14 joules. So that is the second part of the question finished, and that part there got us 21 marks. So the final part they ask about mesons. So it says a member of the meson family consists of two particles. So it says each particle is composed of an up and down quarks and their antiparticles. And we're asked to construct the possible combinations. So combinations of mesons compose of up and down quarks and their antiparticles. So the combinations we can have is up and the anti-up, up and the anti-down, down and the anti-up, down and the anti-down. So the charges of these give us 0, plus 1, minus 1, and 0. And their names then, they are the pion neutral, the pion positive, the pion negative, and again another pion neutral. So you can find these in the tables. You don't have to remember them as such. The last parts then say deduce the charge of each which is given and identify each combination. So that's that there. And the last part is name the Irish writer who first thought up the name quark. So the name quark was coined by the scientist Murray Gell-Mann, who took the name from writer James Joyce. So James Joyce wasn't a physicist, he was just a writer, but he used this term quark. So Murray Gell-Mann took the name from the works of Joyce. So Gell-Mann proposed that there were 3 quarks. It turns out there are 6, but that's why quark stuck. The line from Joyce is 3 quarks for muster mark. So the fact that there were 3 quarks, Gell-Mann took that name of quark and gave it to them. So that was the inspiration. But if you want to say it, at least the charges are in thirds. So if you look these up, the charges of each are in thirds. So there is that little aspect. So the 3 still stands for that. So that is a little bit of a shorter question, but a bit more dense perhaps, especially in this area with your particles. But they're the kind of things you need to know. It's a bit more tedious to learn off by heart, but it has to be done because it could well be asked.